Okay, let's get going here. So, project number 5, were there any questions regarding it? Okay, then today we will continue in chapter 5. You can see what we're doing for the rest of the semester. Basically, we'll do section 6.5, we'll do course evaluations, final exam review, and of course we will have a final exam. This final exam will be comprehensive. With a little bit more of a weight in the exam on the stuff that we've done since test number 2, since you have not been tested on it. But it still will be comprehensive. Are there any questions before we get going here? Okay, so we were talking about overdispersion and ways to handle it. And in particular, we looked at, let me bring up Windows Journal here. We talked about 5 different ways to handle it, where the first 3 ways were the preferable ways. And then if you couldn't do any of those, then look at these final 2 ways. And the final 2 ways were quasi-Poisson regression models. We were just talking in terms of a count response that would be normally modeled in terms of a Poisson random variable. And then also a negative binomial regression model. And the way that they handle overdispersion is as follows. So overdispersion exists when you have more variability in your response than what you would expect if the Poisson distribution was truly correct. And so what this does is it takes variance of y and sets it equal to gamma times expected value of y, where what we try to do is estimate this gamma there. So it allows your variance to be higher than the mean, because again, with a Poisson random variable, the variance is equal to the mean. So that's how it incorporates the effects of overdispersion. And then, we saw the effects in terms of, let's say, estimated variances of our beta hats. What happens? Those variances are higher than what they would be normally with just a regular Poisson regression model. With a negative binomial, though, you approach it this way. Of course, expected value of y is equal to mu. Mu plus mu squared divided by k is our variance. And so we can see that as k decreases, it allows you to have more variance. And both gamma and k are things that we want to estimate. Excuse me. Now, when R estimates one of these negative binomial regression models, it uses glm.mb as the function to do it. And rather than estimating k, it gives you an estimate of something called theta. And all that theta hat is 1 over r k hat. Okay, so it just estimates the inverse of what we were interested in. And so what this means then is that mu plus mu squared times theta then is essentially the relationship that R is using. So we can see that as theta goes to 0, that says that our overdispersion is becoming less and less and less. As theta is increasing, it becomes more and more and more. So then as kind of a general way then to determine, well, do I have an overdispersion problem? What one can do, this kind of is where we left off then on page 578, what one could do is look at the output that you get from glm.mb, and you're going to see the estimate of theta given to you, 0.905 this was for the horseshoe crab data problem. But you also see an estimated standard error. I should just say that, a standard error. The square root of the estimated variance of theta hat. And so as kind of just a general sense of, well, do I have an overdispersion problem? What one could do is take 0.905 minus 2 times 0.161. We're using 2 standard deviations essentially. And if that is still above 0, remember when theta is equal to 0, what happens? Well, theta is equal to 0, variance of y is equal to mu. So you're back with just a regular Poisson again. So if theta hat minus 2 times the standard deviation is greater than 0, that says, yeah, it looks like you do have an overdispersion problem. And so we can see that indeed that's what happens here. You can even do 3 standard errors too. It's kind of an ad hoc way to do this. And the reason why it's kind of ad hoc and I'm not necessarily doing a formal test is because notice what we would be interested in testing. Theta is equal to 0 versus theta greater than 0. At theta equals 0 is essentially on the borderline what possible values of theta are. And when that happens, that leads to problems in doing these distributional approximations. You'll see some other examples of that, especially in section 6.5. So, some other than general comments. Well, we can use likelihood ratio tests with our negative binomial models because we are using likelihood-based procedures. So that means also we can use the 2 ANOVA functions to do our tests that we would normally need to do. So that's good. Confidence intervals for our parameters. We can use confident for profile likelihood ratio. We can use confident.default for walled intervals. We can find confidence intervals for mu using the predict function, just like what we've done before in chapter 4. So if you remember in chapter 4, there was a particular function I wrote called ci.mu. Where did that go? Sorry. Here's the function right there. I wrote this function ci.mu that you could use to find estimates of mu and also the corresponding confidence intervals for mu, where you just pass in your new data, your model fit object. So here in this case, you could use it with a negative binomial regression model. Just put the output from, or the object where you saved the output from glm.mb, put it right there, and then specify your alpha. It finds your predictions. It does the lower bound and upper bound, and then returns both the lower and upper bound. So I applied that to this horseshoe crab setting just to see what would happen for the negative binomial regression model that we did last time, the quasi-Poisson regression model that we did last time, and then also just a regular old Poisson regression model. Save the results, put it onto a nice little data frame, and this is what I get. This was for a width of 23 for the female horseshoe crab. And so with using a regular old Poisson regression, you get 1.33 to 1.92 as the 95% confidence interval. For quasi-Poisson, look what happens. It's a little bit wider because it takes into account this extra variability in the data that does actually exist. The negative binomial also is a little bit wider than the Poisson as well. Notice though it's a little bit shifted though in relation to the quasi-Poisson, and that has to do with these 2 different kinds of relationships that it's assuming. We'll talk about that more shortly. Well, what about at 33 yards? 33 yards. We're not doing the Placekicking data set here. 33 centimeters for the width of the horseshoe crab. Do note that 23 was about the minimum width in the data set. 33 is about the maximum width in the data set. So if I did 33 here, here's my Poisson regression model. That's what that gives me for the confidence interval for mu. We can see with the Poisson regression model, again, it's wider. And negative binomial is essentially even a lot wider and shifted a little bit. Okay? Well, why is this? Well, so you can see the effect that overdispersion does have on your data. Unfortunately, we do have these other methods that are available to us to take that into account. So again, I would expect that these kinds of intervals that we see here to have a true confidence level closer to the stated 95% level than just using regular old Poisson regression itself. And how could you confirm that? Do a little Monte Carlo simulation, similar to what we did back in Chapter 1. And also, there was a nice Chapter 4 example of that too. Okay, so why is this occurring? Oops. Well, notice the effect that overdispersion has for these two different cases. So always with the quasi-Poisson, you're always essentially going increasing by the same amount. It's a linear relationship between the variance and the expected value, a linear relationship. But look what happens within the negative binomial. Once your mean is growing, then that's going to put a bigger effect than that overdispersion has here. And so essentially that's what we were kind of seeing then with the horseshoe crab data, where we saw that we had a wider interval for those larger mu values for the negative binomial versus the smaller values. And we saw then the effect with respect to those intervals. Well, what about taking a look at the residuals for the negative binomial regression model fit? Well, you can still use the same kind of code that we did earlier in Chapter 5, like use R standard, for example, to find the standardized Pearson residuals. And so I plotted the standardized Pearson residuals versus mu hat. And what we can see here, if you remember what it looked like for just a regular Poisson regression model, we had a lot more standardized residuals above 2 than what we do here. And so we can see that the negative binomial regression model did help, similar to what the quasi-Poisson helped as well. So then, how do you choose between these different options that we have? We have 5 options for handling overdispersion. Well, again, as I said at the very beginning, what we said last time too, is that the first 3 options, which were look for another explanatory variable, which helps explain this variability that's not necessarily accounted for. That's the best option. Look to see if maybe it's a zero inflated problem. Maybe you observe more zeros than what you would expect, which can happen with Poisson data, definitely. And then third, you can use a generalized linear mixed model, which we were talking about in section 6.5. So again, those are the top 3 choices, and if you can't do any of those, then you fall back to the quasi-Poisson and negative binomial. And what it comes down to in terms of trying to pick between the two, it comes back to, again, this variance and mean relationship that we just saw. And there's kind of an ad hoc way to help make a decision between the two. This was suggested back in 2007, where, again, notice that I have a simple linear relationship between the variance and the mean for quasi-Poisson. But essentially, look what happens with the negative binomial. I have this squared relationship there. So what they suggest doing is simply plot your squared residuals, which is a measure of the variability that you have essentially left over after accounting for your explanatory variables. Plot your squared residuals versus the estimated mean that you get from a regular old Poisson regression model fit. If you see a linear relationship, oh, okay, quasi-Poisson. If you see more of a quadratic relationship, maybe negative binomial would be better. Again, this is kind of an ad hoc method, but at least it gives you some kind of tool to help try to make a decision about which would be best. It's not necessarily perfect. So let's take a look at how we can do this. So how about we create a new data frame where I have my squared residuals in it. So I'm going to use the residuals function as we've done before, using the model fit from a regular old Poisson regression model. And I don't know if we've seen this before. If I say type equal response, that gives me just the flat residuals. So the observed response minus mu hat. I square it. Also in my data frame, I'm going to put mu hat from the regular Poisson regression model fit. Next, to help me with some visualization of possible trend, I'm going to estimate a regression model that has the squared residuals as the response, and just mu hat as a explanatory variable. And then I'm going to do exactly the same thing, but now with also mu hat squared in it. That's just to help me visualize some trend. If I do a summary of the fit from the quadratic model, notice if I to do a regular old t-test to assess the significance of the beta corresponding to that squared term, notice it's not significant. And notice also it's negative there. Take a look at that. Positive. So just from looking at output, you might be thinking, uh-oh, I don't think I have the negative binomial situation occurring. So now I'm going to do a plot. I'm going to put mu hat on my x-axis. I'm going to put the residual squared on my y-axis. I'm going to use the curve function to plot both of those estimated linear regression models. Put a nice, well, I did ask for a legend, but I don't see a legend there. I'm not for sure.
X and Y are too large.
Yeah. Not sure what happened there. So, my error. Let me make a note to myself to change that in the future. The blue line obviously is the linear regression line, and the red is the quadratic. And so what we could see here, it's kind of difficult. I mean, I guess if you just focus on the red line, you can see obviously it's pointing down. We don't have a positive quadratic relationship like what we would have with the negative binomial. So just from this, I give a little bit more weight to the quasi-Poisson. Again, it's not a perfect tool, but it is one tool to use. Are there any questions? Okay, so what about, so we've been focusing on Poisson data, that kind of count response. But what happens if you look at count responses from a binomial or a multinomial setting? You can have overdispersion with those two. It happens less than with the Poisson situation. That's one reason why I decided not to focus on it in this set of notes. Another reason is, well, you just don't have time to do everything. But you can have overdispersion with binomial and multinomial responses. So in the binomial setting, let's say that we have, let's say we don't have any explanatory variables at all, and we're just simply observing. How about we call it W as our response? We, at least in chapter 1, we often use W as our binomial response. And maybe we always have, let's say, n equal 10. So at n equal 10, we observe, let's say, 2 successes. And also with n equal 10, we observe now 4 successes. And we keep on doing this. You don't have to use the same n all the time, but let's just say that I am. And what overdispersion is saying is that the variability of those W values is more than what I would expect if this data was truly binomial. Meaning that if I somehow knew what pi was, I could compute n times pi times 1 minus pi and compare that variance to the observed variance for the W's. And if that observed variance from the W's was larger, well, then that means I have overdispersion. So In the most extreme setting, though, in the most extreme setting, let's do one more here. We would observe something like this. Now, why would that be the highest variance that I could have? I'm essentially at my extremes. So this shows you this would be the most extreme possible variance that I could have. This would be an example of overdispersion. What you could do is, outside of class, suppose you choose pi equal 0.5. Calculate calculate 10 times 0.5 times 0.5. Then calculate the old sample variance formula for those 4 W's. And you'll see for those 4 W's it's going to be higher than what it is for a binomial. What it should be for a binomial, I should say. Okay. Now, what can you do? Well, you can do those 5 possible ways to handle overdispersion like what we talked about at the beginning of this section. Look for another explanatory variable. There are zero-inflated binomial regression models. They're not as popular, though, but there is zero-inflated binomial regression models. You could use a generalized linear mixed model, and again, section 6.5 will talk about how to do that. Now, in terms of a quasi-Poisson regression model, there are what are called quasi-binomial regression models. And it's based upon the same ideas as the Poisson setting. To actually estimate one of those kinds of models, you can use the GLM function, and you put family equal quasi-binomial. This would be like a logistic quasi-binomial regression model. In terms of the counterpart to a negative binomial regression model for Poisson, what we would normally think of as Poisson data, what you can do instead is use what's called a beta binomial regression model. I'm not going to get into details of why that occurs, but there is something called a beta binomial regression model that will help you to take into account that overdispersion with binomial counts. You use the VGLM function in the VGAM package to do that. Now, overdispersion cannot be measured when there are only Bernoulli responses. But why? It goes back to my extreme example here. If I have Bernoulli responses, my n's are equal to 1 only. My w's are equal to 0 or 1, the most extreme. So you can't really measure that. With respect to a multinomial set of responses, you can, of course, to have overdispersion. And in particular, if you want to look at a function that will help you handle that, there's a multinom-rob function, or multinom-rob function in the multinom-rob package. Okay, so that concludes overdispersion. Are there any questions? So section 5.4 of my book has 2 case studies. So it basically takes you from the beginning of getting some data and starting to analyze it to the end, where you have found a great fitting model from examining a number of different possible explanatory variables, and now you need to interpret that model. One of the examples, one of the case studies, deals with the alcohol data set that was in chapter 4. I didn't actually do that I didn't use that data set in class, but it was covered a lot in the chapter 4 of the book. The other example deals with the Placekicking data set once again, and that's what we're going to go through here. And the reason being is because, while obviously you're going to see some similarities to what we've been talking about before, I think it will provide a nice, let's say, closure to using the Placekicking data set in terms of finding the best model, given that there's a lot of explanatory variables. Now, the data set that I'm using is actually a little bit different from the one that we have been using in the past for these examples for Placekicking. There are 13 more observations in this data set that we are going to use for this section 5.4 example. I will talk about what those extra observations are as we go through this, and you'll see why in the end I end up taking out those 13 observations of my data set. Also, there are some additional explanatory variables that we haven't seen before. There's altitude, which is the altitude for a particular city where the football game is being played. There is a home variable. Is it a home or away for the place kicker? There's a precip variable. Is there a precipitation falling at game time or not? And there's also a temperature variable as well, where I have to assume it's 72 degrees inside a dome stadiums because I didn't have temperature information inside of dome stadiums. Now, and I kind of said this before, this place-kicking data set originated from when I was a master's student at Kansas State. And for my, what will be equivalent to my master's project that students here do for a master's degree in statistics, I basically did a very comprehensive examination of the data. I ended up writing like a 120-page book on it. It was double-spaced and there was a lot of figures, but it was still 120 pages. If you want to see the full analysis, go to Interlibrary Loan and get my my actual book on it. A nice little summary, of course, is in my Builder and Logan Chance paper from 1998. We will be looking at some elements of that paper shortly. Now, so when I was actually doing this was back in spring 1996. And there's obviously been research since then, almost over 20 years, almost 20 years. There's been some research done since then, and and so some of the approaches that I would use to analyze this data nowadays would be actually a little bit different from the way that I approached it in my master's project and then in that paper. In particular, I use stepwise variable selection methods to help me choose amongst all these variables that I had available to me. While that is a possible approach, it's not as good as using, and actually I use a hypothesis test, likelihood ratio test to make a decision between keeping a variable or not. Research now has shown that using an information criteria measure is much better to use. Also, research has shown that these stepwise methods are not necessarily always the best. It's better to use, let's say, essentially look at all possible models and make a decision. And so, because of that, I'm going to approach this in a more modern way than what I did for my paper. Fortunately, though, that the same model that I got into my paper results now. If I use the AIC or the corrected AIC. If I use the BIC instead, I do get a different model. So here are the steps that one could take with this data set now. Okay, so I want to first deal with variable selection. So, here's my paper. The page 21 of the paper, you can see all the variables that I looked at. There's quite a few. I think there's about 12 or so. And I need to choose amongst those variables to decide which ones I should include in my model. And so to do that, and also I need to figure out, well, do I want to include any kind of interactions? And we're just going to simply cap the kinds of interactions up to two-way interactions in terms of interpretability, in terms of what would make sense. And I'm not going to look at all possible two-way interactions. The reason being is because as a football fan, and while I'm not necessarily an expert, I am, I guess you could say I'm an expert football fan. I'm not necessarily an expert with football. But I know some interactions just don't make sense in the context of the data. And so when I was writing up the book and redoing the analysis here, I decided to only look at the following interactions. Like, For example, distance with wind. We've seen that before in chapter 2. That makes sense that you know, the longer the place kick, the more of a time that wind could affect the probability of the success or failure of the place kick. So it makes sense that there would be some kind of interaction there. And so I just simply went through every single possible pairwise combination of all the explanatory variables. I say, okay, this makes sense, this does not make sense. This makes sense, that one makes sense too, that one does not. Some may disagree with my choices. You know, that's reasonable. But I think all these interactions are justifiable, and also I think all the interactions that I did not choose are justifiable not to include. And that's the key with any kind of research, that while somebody may disagree with you, you need to be able to justify your answer. And as long as somebody disagrees with you and they see your justification and it makes sense, okay, fine, we just disagree. Let's move on. That's a common thing in research. So, I need to choose amongst all these, you could say, main effects in these two-way interactions. Now, there is a nice little argument in GL multi, if you remember that function that we used earlier in chapter 5, that allows me to exclude particular interactions that I do not want to consider. Unfortunately, I came across an error in the function. The function does not work well when you have lots of interactions you want to exclude. And I'm 95% confident that it is truly an error, because I have really tried it a number of different ways. I couldn't get it to work. I looked at the code for it. I could not get it to work. So, well, what can I do now? So what I decided to do then was, I'm going to use GLM multi then with just the main effects, because that did work. And then I'm going to use forward selection amongst the possible interactions that I'm going to consider. I thought that was just a good compromise of how to approach this. I decided to use the corrected AIC. I could have made it a lot easier on myself by just using the regular AIC. But I guess for some reason I decided to make it hard on myself and use the corrected AIC. The reason why it was hard, you'll see shortly. In the end, I would expect the same answers to occur because I have a very large sample size. So, to begin here, I read in my data set the usual way. And then in order to use the GL multifunction, I need to first estimate the model that has all the main effects, essentially, in it. So I do that. This is nothing new. And then to use GL multi, I put in for the Y argument, the mod.fit from fitting that very big model. Level equal 1, if you remember, that corresponds to I just want the main effects. Method equal H means exhaustive. So I want to look at all possible combinations of the main effects. The information criteria I'm going to use is the corrected AIC. And then, of course, the family equal binomial, link equal logit. So I tell R, go do it. And after a while, notice how many models it looks at. More than 2,100. I get this. I can do a nice little summary of my output in a very similar manner to what we've done before. And we can see that the best model in terms of the corrected information criteria, by meaning it has the lowest corrected AIC, is the model has distance, wind, change, and PAT in it. Now remember, change is a variable that's essentially measuring pressure. 1 for pressure, 0 for not pressure. Notice that PAT is in there. And remember, we saw some issues with the PATs when we were just looking at a model with distance before. Also, that weights, the weights column there, sorry, the table didn't fit in very well here, but that weights column, that basically gives us a measure of what's the probability that this is a correct model. And we can see by looking at the corrected AICs and that weight column there, that we see a lot of models are quite similar to one another. And so what would be a possible way that one could, maybe an alternative approach that one could use here? Yeah, the Bayesian model averaging. I did not do that, but that would be, when you see something like that, that says, hey, that's something that, maybe if you want to go that route, that's something that you could explore. Then when I use the print function, as we've done in the past, we can see that, let's see, where is that? There are 20 models within 2 information criteria units. And we saw that earlier in this chapter, that often that's kind of a dividing line that's quite often used for determining, well, are there a lot of models that are similar to one another and how good they are? It says about 20 are. Okay, so now I have essentially a model to start with. And now I want to look at, well, are there any interactions I should include? And I'm going to continue using the corrected AIC. Unfortunately, there's not a nice little function R that will automatically calculate that for you. So I wrote my own function. And this is one reason why I kind of did the corrected AIC here, because it shows you, simply how you can extend the functionality of R rather simply. Also, you might be wondering, well, why don't I just use the step function? Well, the step function doesn't work with the corrected AIC. Again, if I wanted to make my life simpler, I would have just used the step function. But this is just a nice little illustrative tool for a classroom setting. So that's why I decided to do that. So first, I'm going to estimate my model that just has those 4 explanatory variables in it. Notice I get a corrected AIC of 780.8063, which is what we had saw previously in the output. With this function too, because I was doing some various other things in my program, I decided to also allow it to calculate the BIC too, and there's the BIC. Now, since the step function, as I just told you, doesn't work with the corrected AIC, I essentially have to go through the 4 stepwise selection by hand, you could say. Meaning I have to estimate every single model myself, one at a time, and look to see how, or calculate the corrected AIC, and then compare it to the original model itself. What I mean by that is as follows. So for my first model, distance, wind, change, and PAT, just like what we did before, and the first interaction I want to examine is distance and altitude. Since altitude is not already in my model, I'm going to add altitude in there. I get the results and I put in mod.fit1. I do that for all 12 possible interactions. Notice the last one, distance, wind, change, PAT. And then I want to look at the precip and temp 72 interaction. Notice I had to add the main effects to the model as well. Once I get that, then I'm going to extract all the corrected AICs from my model fit objects by using my nice little function that I've created. I put all those corrected AICs into a vector, and for labeling purposes, naming purposes, I create an object called enter that tells me, well, which of those interactions are being examined. So remember that first model, distance and altitude. Obviously, there's a lot of code details here. I'm just kind of giving you the big picture here. When you step through it on your own, I don't think it's going to be too difficult to figure out what's going on if you still have questions. Okay, let me actually go to my program. So there's something I want to show you that might be new to you. Probably is new to you. Okay, so here's all my names of my interactions. and here are all the corrected AICs. I'm going to put everything into a nice little data frame. So there's my data frame. And what I'm looking for here is, well, which of the corrected AICs are the smallest? That will tell me which interaction included in my model. Of course, the smallest AIC, too, needs to be less than my original corrected AIC that I had with the model without interactions. To help me find the smallest corrected AIC, what I'm going to do is do some sorting. Now, there's not a nice little proc sort like you have in SAS that's available in R. So to do the sorting here, I'm going to use a function called order. So I'm going to say order where my my corrected AICs are. Remember, it's the second column. And what this tells me is that my third element, this one right there, is my lowest corrected AIC. My sixth element, which is this one right here, is my second lowest AIC. So using those orderings there, I use that as essentially then the row numbers to return to me for my data frame. And so that now I have everything nicely sorted. Any questions about that? It's a little bit of a roundabout way to do it, but it works quite well. Okay. So, hold on a second. So what this tells me is with distance and wind, that when I add distance and wind to my model, this is the most important interaction essentially. And my corrected AIC is 777. Before it was 780. So I have indeed improved my model. What that means then is I'm going to add the distance and wind interaction to my model. Now the next thing that I'm going to do then is that once I have distance and wind in my model, and some of this code is not in your program, I'm sorry, in your notes, then I'm going to look at, well, are there any other interactions I should include? So now I do a second, you could say, stage of this forward selection, where I have distance, wind, change, PAT, distance by wind, and now I'm going to look at, well, should I include distance and altitude? So if I do that, I need to include altitude there as well. Put that in there. If I did AICC mod.fit 1.2, I get a 780.875 value. Do you think I should include distance and altitude? No, because it actually increased my corrected AIC. So I go through all these interactions that are remaining, making sure that distance and wind is still in my model. Then I put everything into a nice little data frame. I sort it, and this is what I get. Distance and PAT. When I add that interaction to the model, I get a corrected AIC of 773. That is lower than what we had previously. So I have found an important interaction. Once I get that done, I look at, again, all my interactions that are remaining. So notice I'm going to have distance and wind, distance and PAT in there, but now I'm going to start off again with, oh, it's distance and altitude important, where I include the altitude main effect in there. So let me go ahead and do that. And distance and change has the lowest corrected AIC, but this is higher than what we had previously. So I stop. I have, in the end, added just 2 interactions to my model through this process. Any questions? Takes us to page 593 then. So essentially what I have now is, you could say, a preliminary model to move forward with. So I have the 4 variables with 2 interactions in there. Now I want to really emphasize here that there were alternative paths I could have followed. And they are justifiable. Remember what I was talking about earlier. Very frequently, you give a data set to one person, and tell them go find the best model possible. Give a data set to another person, tell them to find the best model possible. Do it for a third person too. Same data set. Often what will come back is different models because there's more than one approach. The key is you have to be able to justify what you're doing. And there might be more than one justifiable approach. So another approach that could have been done was I could have used that genetic algorithm, remember that will allow me to search amongst all models that has the main effects and all possible pairwise interactions in them. I couldn't do an exhaustive search because it's just too many pairwise interactions. It would take too long. So instead I could have done the genetic algorithm to search amongst all these possible models. I did do that. What I came back with was some models that had interactions in them that was like, I can't justify that. I could tell our coach, Coach Riley, hey, you should have this interaction in your model. And he'll say, what? Don't you know anything about football? That doesn't make any sense. And so because of that, I did not think that that was a good approach. But if someone else did do it, I can see that's possibly justifiable. Also, you could have used the BIC instead. Now, if you were to use that, you remember the relationship between like the BIC and the AIC. The BIC typically will have smaller models. And in fact, you do have a smaller model here. All you end up with is just distance and PAT. That's it. That is a justifiable approach. One should not use the BIC just because your model is going to be smaller. You got to be careful about that. I kind of thought of this as more of an exploratory study. So in that context, I'm not necessarily concerned with having other variables in my model. That might be, let's say, maybe kind of marginal. Should I include them or should I not? So I thought of this more as an exploratory study. No one had ever done this before. So that's why I was definitely comfortable with using AIC, despite knowing that I'm going to have probably a larger model in the end. Okay, now let's look at if we can improve our model. What I mean by that is, well, maybe we need some kind of transformations of these variables that are currently in our model. Maybe quadratic terms. So, we looked at previously that maybe a distance squared term might be helpful. Remember, we kind of had a borderline p-value for a likelihood ratio test back in chapter 2, when we just had distance and distance squared in the model. Well, what about other transformations of the other? How about transformations of the other explanatory variables, like wind? Do you think we should have a wind squared in our model? No. Why not? Because it's binary, yeah. 1 squared is 1. Well, that's not fun. What about change? Well, change is binary. What about PAT? PAT is binary. So, the only transformation that I can really justify looking at here, or at least makes sense, I think is like the distance squared, and see where that takes me. So to do this, first of all, before you even do that though, what you should do is maybe you can say a preliminary look at your residuals and see if maybe you see some kind of trend in your residuals. So what I'm going to do is first convert my data to explanatory variable pattern form. We've done them in the past, but not with as many variables as we have now. So it's very simple. I use the aggregate functions we've done before. We've had formula equal good tilde distance. And then I just simply use, similar to what we've done with like the GLM function as formula argument, I put when change in PAT in there. And I'm going to summarize or aggregate by the sum function to find W is going to be my number of successes. Why don't you think I need to put in the interactions in there? Excuse me?
Doubling, because they're already kind of considered with the.
It's not going to change anything. It's not going to change the unique number of combinations of your explanatory variables. So that's why we don't. Okay? I mean, if you did, you get the same answer. Well, I think you should. You would. I just don't know if the function would run or not. I've never tried it. So then I find the number of trials at each explanatory variable pattern. For each explanatory variable pattern, I put everything into a data frame called W.N. And this is what I get. So at a distance of 18 yards, when is 0, change is 0, PAT is 0, 1 success out of 1 trial. Now remember, in the past we saw 3 trials at 18 yards. Well, that's because we only have 1 now. Here, it's because only 1 for when 0, change equals 0, PAT 0. I believe it's for change where the other 2, when change is 1, distance 18, when 0, PAT 0. I believe that's where the other 2 go to. I guess if we really wanted to, we could see it. So I didn't explain that very well. Let's see. There we go. So we have 124 unique explanatory variable patterns. Let's find 18 yards. Here's the other 18 yards. Yeah, it's for change. Change equal 1. So we have 3 place kicks with a distance of 18 yards. One of them has a change of 0. 2 of them have a change of 1. Okay. And let me come back here. Now, whenever you convert to explanatory variable pattern form, just as a way to test to make sure that you indeed did it correctly, you should estimate the model using this new data set. Of course, using weights equal trials, and also good divided by trials there. So we have this binomial format. And indeed, this is exactly the same model, even though I hadn't shown you before. It's exactly the same model as we get with the binary format of our data. Okay, so what about then looking at transformations of distance? So what I decided to do was calculate some just regular old Pearson residuals, just to give me an initial impression. And I'm going to plot them versus the distance. So this is the plot that I get. I put a low S regression model on it as well to help me detect any trends. So we can see that there's not a whole lot of I did do standardized Pearson residuals, sorry. There's not a whole lot of standardized Pearson residuals that are outside of plus or minus 2. There's none outside of plus or minus 3, so that's good. That's saying a lot of good things about our model. Think about what we had before when we just had distance in the model. But also, we don't see any trend here either. So what this is saying to me is that, hey, I think distance is okay the way it's at. Now, for emphasis, and this is something that you would talk about in a course like Stat 8 and 70, I just want to make sure you understand why this occurs, and we might have done this a little bit before. But let's talk about one potential trend, a particular trend that would tell me, hey, a quadratic term might be possible. And let's do it in the context of simple linear regression. Shoot. I guess we can go with that. So let's say I have X, I have Y. Again, simple linear regression. And let's say I have a scatter plot that looks something like this. So my point is that it looks like there's a quadratic trend, although my points are not very much like points. But if I were to estimate a simple linear regression model, so just a straight line model, this is what I would get. Something like that. Now translate that into a residual plot. So here is, let's say, x. Here is y minus, we'll call y hat as our predicted value. Well, in terms of a residual plot, you're going to see something that looks like this. Like a little bit of a linear trend. Why is that? The reason being is because notice how all my residuals, or pretty much all of them, are going to be negative for that portion. And then all of these are positive due to the poor fitting model. That's why I know that kind of a trend means quadratic. The same thing essentially occurs with now this little logistic regression setting. We didn't have a trend, so that's why I feel good about not needing a distance squared term in the model. Now what one could do is actually estimate your model with all your explanatory variables in those two interactions, and then also add a distance squared to the model. And if I were to do that, I get a corrected AIC of 775. The corrected AIC without distance squared was 773. So by adding distance squared, it has increased stuff, has increased that information criteria. So therefore, yeah, I don't need a distance squared term. I'm okay with moving forward. Any questions? Okay. Now what I want to do is assess the model fit with this model that I have found with the 4 main effects, the 2 interaction terms. So what I can do is apply this function examine.logistic.reg that we saw earlier in section 5.2. I can apply it to my mod.prelim1, which was the resulting model from estimating the model to the explanatory variable pattern form data. I'm going to identify my points interactively. I'm not going to run through it here, but it's the same thing as we've done before. I'm going to scale the plotting points for both my when I do a bubble plot with the bubbles proportional to the number of observations per explanatory variable pattern, and also when I do a bubble plot with the plotting point proportional to Cook's D. This is what I get for those 4 plots. Now, what you'll notice on page 597 is a point-by-point, a plot-by-plot set of comments. And I think that's very helpful for you to do in actual practice, just to type up what do you think about these models? What do you think about these plots? Are they telling you that there's any problems with the model or not? And so if we look at the upper left-hand corner plot here, think also back in your mind about what we saw previously when we only had distance in the model. We did have some explanatory, we had some, I'm just going to call them observations here. We had some observations that had a standardized Pearson residual somewhere down here. I think we had another one up there. Does that sound familiar? I hope so. If not, go back in your notes. But now notice with these extra explanatory variables in my model, I don't have that anymore. Also, we were a little bit concerned about that lowest regression model. Did we have any kind of, we thought, well, maybe we might have some kind of trend. Obviously, we don't. And so, what this is telling me is that some of the problems that we were having before have been eliminated. The reason why is because of that PAT variable that we are having in our model now. That's taken into account. If you remember, or at least one of those potential outliers that we saw was due to the PATs. But also with some of the other stuff that's going on in our model, that's eliminated the other potential outlier as well. Although in the end, we knew we couldn't trust a standard normal approximation to it anyway, because there wasn't that many trials for it. So we have some observations that are outside of this plus or minus 2. Primarily, they're down here. They're not too far extreme. But I've identified those and put a little number by them so that we can come back and look at those observations closer. Okay. Let's go into the upper right-hand corner plot. Remember what we had before when we had just distance in the model. We had something that had a huge Cook's distance to it. We don't have that anymore. We still have a particular observation, though, that has a larger than what we would maybe like. But remember there actually should be two lines going across this plot. One is drawn at, and I apologize, I don't remember exactly. I think it's like P divided by the number of observations. Hold on a second. Actually, this is drawn at 4 divided by number of observations. But we would, this is on page 551. But we should also have a line up here drawn at 1. Notice this only goes up to 0.3. So what this is saying is that this particular observation, number 120, might have some influence. We should look at it more, but definitely it's not as much of a concern as we had with the model with just distance in it. Also, we can take a look at 117. We can take a look at 119 as well, and some of the other ones. With respect to the matrix diagonal values, we see 117 and 120 being quite highlighted. Okay, so we'll make a note of that. We'll come back to it. The bottom left plot is my delta x squared. Remember, that's measuring how much does my Pearson statistic change when I have an observation in the model. I'm sorry, when I'm using a particular observation to help estimate a model versus I'm not using that observation. And again, we see a dramatic improvement over what we had previously with only distance in the model. Remember, we had something that was like, if you look at the scale here, we had something that was like would be like way up there. And instead, in the two, you could say the border lines that we have drawn on there, we don't have anything above that upper one. We do have a few that are between those two lines. And so we might want to look at those a little bit more closely. I should say might. We should look at it a little bit more closely. Remember, the plotting point is proportional to the number of observations at an explanatory variable pattern. So if we see a plotting point that's kind of large and high up on the plot, that would concern us. Yeah, maybe 15. But the other ones, they're drawn at actually about the small as they could get if you make a comparison of all of them, suggesting, and you'll see this in the actual data set itself, these actually have very small number of trials. And that, again, I would not expect a distributional approximation here to work well. Chi-square distribution approximation to work well. Notice where some of the big circles are. Of course, the big circles, if you remember from the past, are probably corresponding to like 20-yard place kicks where we have a lot of PATs there. Previously, we had that big one. We had a big one up high. But now all of them are down low. Why? Again, it's because now we have a PAT variable in our data set, or before we did not. Lastly, the lower right-hand corner plot, exactly the same, except for now the plotting point is proportional to the Cook's D. So it allows you to look at two measures of influence at exactly the same time. And notice how 101 and 15 kind of pop out at you there. Notice too that big circle there. Well, what does that correspond to? 120. How do I know that? Well, obviously, that has the largest Cook's distance and has the largest circle. So what that's saying is that this particular observation is being fit well by the model, although at times that can actually mean that there's actually a problem, too. Why? Again, this is something like in a Set 870 course that you would learn about, but we can talk about it here. So again, let's go back to the simple linear regression setting. So I have y versus x. And suppose here's my data. All my data points essentially follow a nice, sorry, I can't draw today. Everything should follow a nice little linear line, mostly. So there's my little linear line there. But let's say also I have now this additional observation. Well, we'll put it right there. Okay? As we talked about before, that point's going to have an effect on the model. And depending upon what the actual data were, it might be like this. There's my new model with that additional observation. Is my residual going to be large there? No, because that line has been pulled down towards it. So what that means is that this could have a large Cook's distance being influential, but yet have a small residual. Now I'm not saying that that is what's happening right here, but whenever you see something like that, you might be, that should be in the back of your head that that potentially could be happening. Look at my deviance divided by degrees of freedom, 1.01. Hey, this is looking good. Okay, so next what I did was, let me get back to the right spot on my notes here. We are on page 97 and 98. So what I would like to do is now take a closer look at those observations that, were shown to us that, hey, there might be something going on here. Maybe the model's not fitting well, or maybe a particular observation was influential. So what I did was, from my function that I wrote to generate that plot, I saved the results into an object called save.info1. And I can extract important information like my standardized residuals, my Cook's D. I extract all those from that object. And then what I want to do is form a true-false object that corresponds to every single observation that tells me, hey, is this a particular observation that's, let's say, outside our border lines or not? So for example, I look at the absolute value of my standardized Pearson residuals. Are they greater than 2 or not? So if I execute this segment of code here, I'll get some trues and falses. The trues are the ones that I want to take a look at closer. I do a similar thing with my Cook's distance, where I take 4 divided by the number of observations. In other words, I'm looking at, just to make sure this is clear, I'm looking at essentially this line here. I want to find all the observations that are greater than that line. Also, I'm going to do a similar thing with my my hat matrix diagonal values. So I'm going to have 3 sets of trues and falses. Or you can say it this way, I'm going to have 3 trues and falses for every single observation. If at least one of those is true, I want to look at that observation. So the way that I do that is I use a little vertical line here. That means or. So if I come back here to R, oh, unfortunately, I did not run this beforehand. I'm sorry. Here we go. I'm just going to escape out of there. Okay, I should have escaped out of there. There we go. So what check or ck.out stands for is check out. So you can see now when I combine all that stuff together, where I have true corresponds to observations I want to look at further. So that then, when I take my wn.diag1, which corresponds to where all these diagnostic measures are stored, I'm just going to look at those rows that have a true. And then I end up ordering them by distance. And this is what I get. So we can see, for example, observation 60. Let's go back to my plot. So here was observation number 60, right there. So it had a maybe a little bit unusual standardized Pearson residual. It doesn't look like it had any issues with Cook's distance or matrix diagonal values. Just go back down here. Oops, sorry. So here's observation 60. And we can see that there's that standardized Pearson residual, negative 2.57. Notice I only have 2 trials at that distance, so I know that a standardized normal distribution approximation is not going to work well. So I'm not really concerned about this particular observation. Let's move on. So let's look at some more interesting ones. Number 120. So 120 is the one that really stuck out. Okay? Had a large Cook's D. Let's see. I'm going to do a different highlighter here. So 4 trials, 3 successes. Look at that Cook's D, 0.31. By far, it's greater than anything else. And let's look at the remaining parts of this explanatory variable pattern. Distance 30, wind 0, change 0, PAT 1. Is that unusual for football fans? Tell me, is that unusual to have something like this? Yeah. I have a PAT, which are normally 20 yards. I have a PAT that's actually 30 yards. When can that happen? Yeah, suppose I have a penalty. Maybe there was holding on the offensive line, for example. So he lost 10 yards, had to re-kick. This is very, potentially this could be very influential here, and we have identified an unusual aspect of that. Let's take a look at number 119. There's 119. It also had kind of a larger Cook's distance. 29 yards, it was a PAT. 0 successes, 1 trial. This is odd again. And supposedly this is influential, or I should say again, potentially influential to my model. Now we're running out of time here, so I'll just say you can go through these other ones, and most of the time, you can say, yeah, I have very few trials, so I know a standard normal or a chi-square approximation is not going to work. Why can't I say this for number 119 and 120? Well, Cook's D doesn't use a distributional approximation. Sometimes students get that mixed up. No, I'm not using a distributional approximation with Cook's D. We see some potentially, let's see now, so like this one, 614, I'm sorry, 117 here. Notice it has a Cook's D of 0.06, so if you look at the plot, you'll see it kind of sticking out a little bit. Well, yeah, I would expect that one to be influential because there's 614 observations there. So I'm not concerned about that. I had a little bit of concern about number 15 here. Remember that one? 12 successes, 18 trials. Its standardized Pearson residual was negative 2.67. So it's a little bit more extreme than what we expect. The standard normal approximation is probably not going to work too bad there. So maybe we want to follow that up a little bit further. But again, about 5% of your observations should have standardized Pearson residuals outside the plus or minus 2 range, if indeed a standard normal approximation works. So I have a little bit of concern, but not a whole lot. But I definitely have concerns about these two. And so what we will do next time is investigate these two more closely and figure out what's going on with them. Why is this causing this kind of an issue? Any questions? Okay, that's it for today.